Progress. Thank you. All right. So, hello everybody. Welcome to AC219AS, Secure and Advanced Computer Architecture. My name is Nader, and will be your instructor this year for this course. This is the second time we're teaching this course, so we kind of got some good feedback last year, and we're looking forward to continue that this year. All right, so plan for today is I'm going to do a brief introduction about the logistics. Most of you have taken courses with me, so you're probably familiar with a lot of these things. So for those of you who didn't, and there are a few things that are different from this course and other courses that I teach, so I'm going to talk about that. If you have some time, we're going to also talk a little bit about some basic concepts and why this is an important topic and things like that. So the main question we're trying to answer in this course is this fundamental question that is hardware safe. And we're going to talk about various different things to answer this. And for that, we also kind of take a step back and talk a little bit about computer architecture and hardware design itself. But the short answer is no, unfortunately. And in order to understand that, you have to kind of, again, take a step back and kind of ask a more detailed question, as in, what is the formal definition of safety and security? What are the assumptions? What are the goals of the adversary? So there are things that the adversary can do, and there are things that the adversary cannot do. So depending on what you want to achieve, you can assume that the hardware is safe, and you can assume the hardware is not safe. But the main thing about security of computer architecture particularly is that for a very, very long time, we thought that the answer to this question is yes. And we mainly were negligent about designing and putting security features in our hardware when we're designing systems. And that kind of unfortunately put us in a very, very tough position right now, that there are many, many features, advanced features that we are using, but none of them are secure. And we cannot really disable those features, but we cannot also use them. So it's kind of like, iffy situation. So in order to understand that, this course is basically first tries to teach you those features. Some of them you already know, some of them we go a little bit more in depth, and that's the advanced computer architecture part. Well, then once we learn those features, we're going to learn about the security and why those features are not good things for security and how adversary can exploit them. And then we're going to also talk about what we can do now. Like, now that we're in this kind of mess, what should we do in order to fix it? So that would be also part of the course that we're going to talk about. So as I said, we're going to talk beyond security. So this, I would say 50% of this course is about security. The other 50% is really not about security. It's about the common things that you see in designing any computer architecture, computer systems, including performance and overheads and power. So you're going to see a lot of that, especially in the first half of the class. We're going to mainly talk about non-security stuff. So it's kind of like a balance between security and non-security. Our focus is going to be on the computer architecture. So we're not going to go deep into hardware and talk about like circuits or transistors or physical design. We're not going to go very high level in talking only about applications. We're going to kind of stay in the middle layer. So we're going to talk a little bit about like market architecture, ISA, a little bit of software, but that's what would be our main goal. And this picture is showing the abstraction layer that you start all the way from electronics and IC and transistors and gates and registers. But like blue and up is where we're going to mostly focus in this course. But of course, when we're talking about particular layer of abstraction, you also have to have a good understanding of other layers. So for example, you have to understand how operating system works and a little bit of like, how the circuits and underlying transistors work. But as I said, we're not going to directly talk about those things. Most of you already know you have taken a few courses in those topics. But if you have a general understanding of computer systems, that should be enough for you to follow along this course, okay? So as I said, this is secure and advanced computer architecture. So the main focus is computer architecture. We're going to talk about security stuff, and we're going to talk about advanced feature stuff. So it's kind of a mixture of both, as I said. So the class format. So the class format is regular lectures. So I'm going to come here every week, every lecture and lecture. It's less about homeworks and exams. So this is a grad class. As I said, those of you who are taking courses with me, especially the grad courses, you know that this is more of the style is for you to giving you some bits and some information, and you're gonna go and read it by yourself. So it's gonna spend some time understanding these things by yourself. So it's not gonna be like, you know, very hard, like, you know, lecture-based course that you might usually see in like a classic undergrad class. There's going to be hands-on projects. We're gonna have 3 or 4 projects. And we're gonna have paper readings and paper presentations. So it's gonna spend a good amount of time reading papers and presenting papers in this class. All right, so let me talk about logistics and feel free to ask questions. Is there any questions before we get into the logistics? Okay. So first of all, about me, I got my PhD from Georgia Tech in computer science in 2020. So this is my 5th year at UCLA. And my research interest is actually this topic that I'm teaching, the computer architecture with emphasis on security and privacy. These days, I also do a lot of stuff on embedded systems, so it's a layer above this. But my main research goals is just security and privacy in general. So many of these topics I'm going to talk about, I've been working on it or currently working on it or work on it in the past. And then at some point, if you get interested in any of the topics, feel free to reach out and see if we can like do some research beyond this course as well. If you have taken courses with me, you know my cats. This is PJ and this is Meta. PJ actually recently had a medical emergency. We took him to the hospital, but he's doing fine now. But you're gonna see a lot of their pictures in the class. How you're gonna contact me is that as you have seen my posts on Canvas, most of you, we're gonna use CampusWire. We're not gonna use Canvas. How many of you haven't used CampusWire before? Okay, a few of you. You just go to campuswire.com, log in. I put those of you who didn't use CampusWire, have you seen my post on Canvas? Okay. So yeah, you just click on it. It asks like there's a link. It asks for your join code. I'll post the join code as well. Just go there and log in. All of the communication and announcements and questions and everything will be posted on CampusWire. So you're not going to see anything else beyond that one post that I posted on campus about this course. Everything will be on CampusWire. So please do it ASAP. Maybe during the break, please enroll on CampusWire. If you have more serious questions or urgent matters, you can email me. Office hours is right after this class on Mondays from 4 to 5 in my office. My office is in Bolter Hall, 6731G. If this time doesn't work for you, right before the class, usually also a good time. Right after the class on Wednesday, also usually a good time. If none of these times works, Friday afternoon is also usually a good time. And you can always message me and schedule a one-on-one as well if you want to. We can also try to find a Zoom time if like in person doesn't work for you. All right. Before we get any further, let's actually talk a little bit about you guys. How many of you haven't taken a course with me before? Okay. So for those of you who didn't, maybe you want to share something interesting about what you did on your break. What did you do in the break? Maybe introduce yourself.
Sure. My name's David. I'm first year master's student in the circuits area. Over the break, I went to Philadelphia to visit my partner.
Nice. How was the weather?
It was not bad. It was a little gloomy to begin, but then like the last day was nice and warm.
Are you from Philadelphia?
No, I'm from LA.
Okay.
Yeah.
Were you a Eagles fan for the Super Bowl or no?
I had to be.
Cool. Anyone else did anything interesting over the break? Yeah.
I actually had a race yesterday, road race, so criterium, I got 4th.
Oh, nice. Okay. Road race as in what?
So like, on a bicycle.
On a bicycle. Okay.
Yeah.
Nice.
And then I also worked during the week, but that's what I did.
Nice. How long was the race?
It was just an hour. It's just a timed race. So
Okay.
it's based off your speeds and who crossed the line first.
Nice. Okay. Cool. Yeah. Anything else? Anyone else did anything interesting during the break? What's the most boring thing you did during the break?
I sorted my entire
Tax
downloads. I
What's
sorted my entire downloads folder.
Oh, wow.
Yeah.
How long does it take?
It took most of the day.
Wow. So what did
I
you,
just
how did
sat
you
down for the
organize it?
entire day. I just
So you
sorted
put them
every file
into
my dad was writing.
folders or?
There were thousands of files in there, and at the end, it felt so sad. It felt incredible.
Yeah, that's really nice. I'm very picky about my download folder. Like if I see 4 files, I'm gonna be very
Yeah,
stressed.
now that's what I'm gonna do. It feels so good to have them.
Yeah, my email counts and my files and downloads. These are my 2 like red
Yeah, I
lines.
cleaned out my email a few years
Yeah.
ago, and now it's always red.
You did your taxes, Philip?
Yeah, I did my dad's taxes.
Oh, wow.
Yeah.
Did you charge him or?
So our accountant is like a terrible person apparently, so we got easy because of like the tax return was really good. And he just would not fill out this 8936. It took me 10 minutes to fill it out by myself. And the accountant guy would just not do it. He actually contacted me this morning again, telling me like the guy did the entire form wrong. So I have to figure it out tomorrow too.
Wow, okay.
Yeah, taxes definitely. was
Some
one.
more boring things.
Yeah.
Cool. Anything else anyone wants to share? All right. All right, so let's talk about the course elements. So as I said, it's the main 5 components of this class is the lectures, of course. There's paper readings and presentations, your participation, there's an exam, and there is computer assignments / championships that I'm going to talk about. By the way, this class also has an online version. So there's actually people who are watching this lecture, the recorded lecture. Hello to you guys as well. So the lectures would be shared between the on-campus and online. Things that I'm going to talk about for the logistics, mostly the same for both group of students. For MSOL students, it's slightly different in some places. I'm going to actually highlight them. So don't be confused if I say MSOL students this, on-campus this. So one applies to you and the other don't, depending on which student you are. Okay. All right, lectures. First few lectures going to be about advanced mark architecture. So we're going to talk about just these advanced features. We're going to talk about out of order execution, and we're going to talk about a lot of features that we use for out of order execution. Then we're going to shift our focus on security, and then afterwards we're going to like kind of interleave advanced mark architecture with security. So we're going to be like some lectures about security and some lectures about mark architecture. We're gonna also then the kind of like final 1/3 of the course, we're gonna focus on memory hierarchy and both performance related concepts and security concepts. We're gonna talk about like caches and memory and DRAM and stuff like that. So in terms of the background that you need to follow along and understand the concepts in this course, this is not an introductory course to computer architecture. So if you have almost zero background in computer architecture, this is not a good course for you, because we're going to build on top of what you've learned in an introductory course on computer architecture. So for example, if you don't know what is an ISA or what is pipelining, then it probably a good point for you to kind of like, know that this might be not a good course. Also, I'm going to talk about a few things in the later half of this lecture and see if like these are too advanced for you. This is not a good course for you. So what are the 2 options and how do you know how much knowledge do you need? So if you really want to learn computer architecture and you don't have any background, my suggestion to you is that there is CS 151 or ECE 116. These are the same courses cross-listed across ECE and CS. This is offered every quarters, and this is the introductory course. So if you want to learn computer architecture, that's probably a good course for you to go and take. And then once you build that, then you come and take this course next year or something. Although next year I'm not going to teach this course, FYI. But if you kind of know a little bit about computer architecture, you can also do a quick crash course in computer architecture. I do teach introductory computer architecture as well. I do it every fall. You can actually go to this link that I shared here. This is the latest. And you can see the lectures and see how much you know. You can watch the videos. All the videos are available. All the slides are available. So you can kind of like see how much you know. We're going to build on top of what we taught there. So that's kind of a good kind of test for you to learn to know whether you know enough. But yeah, generally, I mean, kind of rule of thumb is that if you never took any undergrad level or equivalent of a computer architecture, probably you're not going to do well in this class. So that's it with the prereqs. Technically prereqs for this is, as I said, M116 or CS33 in UCLA. But some of you are coming from different undergrad, programs, so you might have different course numbers. All right. So information about this class is available online. So you go to that link there, you go to S25 index, and then you see everything. The previous version, also, if you go to the teaching page of my website, you will see that there was another offering of this course last year. You can see the topics. Many of the topics going to be shared. And then the videos are there if you want to, if you're really curious, you can watch all the lectures. There will be some things different, so just be careful that everything, it's not going to be exactly the same things, so there might be small changes. And as I said, we're going to use CampusWire, so please enroll ASAP. And we're not going to use Canvas. We're also going to use Gradescope for your exam, for your computer assignments. I have already enrolled all of you, but as you add, intern to the class, you're going to be enrolled. If by next week you're still not enrolled in Gradescope, let me know. Okay, so message me or email me. All right, lecture format is going to be in person. Everything will be recorded, hopefully, so you can watch them. For MSOL, of course, this is not going to be in-person class. I'll try to post everything within 24 hours, usually within the same day, but usually might take a day for me to post things. All the recordings available in this link here. You're going to see the slides. I'm not going to share you the notes, and mainly because for you to take notes yourself. But this raw slides, you're going to see it there. Attendance is not required. It's optional. If you want to come, do come. It's definitely encouraged. I think you learn more by coming to the class. Not just because, you're going to watch the lectures, but also kind of being in the classroom usually help people to kind of stay connected. And you get a chance to see each other and talk to each other and so on and so forth. So use this opportunity for those of you who are in person and doing this either as a master's student or undergrad students. I think it's a wrong decision to not coming to the class and it's understandable if there are lectures that you want to watch it online. Or recorded, but try to come to the class is usually a good practice. Questions during the lectures are very, very encouraged, and please do feel free to interrupt me and ask any questions. Is there any question right now? Yes.
Just to clarify, are you posting the slides or not?
Yes, the slides are already posted.
Okay.
Yes, the slides will be there. If I annotate the slides, then I'm not going to post the annotated version. So you're not going to see this. Syllabus is also already on the website. So as I said, the prereq is the computer architecture class. The list is there. There might be slight changes, but kind of you can see the plan of what you're going to learn if you're curious about. All right, so this class also has presentations by you. Later half of the class is going to be some presentations. We're going to have, I think, 6 different category of presentations, 6 different topics. Presentation is going to be in group because there is a lot of you. So it's going to be a group of 3, 2, 3, or sometimes 4. MSOL students going to be individual because there's only 10 of them. Details on the group and what papers you're going to present and when you're going to present it, going to be posted on CampusWire. So watch out for that post. It's going to be posted this week. You need to basically create your groups and put in your names. So try to talk to each other and kind of form the group. If you don't know anyone, that's okay. There will be a Google form that you need to submit, and I'm going to create a group for you. So if you don't know anyone or you don't have any groups, don't worry about it. So what's the goal of the presentation? The goal of the presentations for you is to go a little bit deeper into a topic. So you're going to learn, you're going to read the paper and you're going to learn it, and you're going to present it for 10 minutes for everybody else. The paper they're going to select are usually latest and greatest in the topics that we're going to cover. They're going to be about security topics. So the way it works is that I'm going to give you the knowledge of advanced market architecture, and you're going to go and learn about these security topics for each one. And then the goal of the presentation is then, transfer this knowledge that you've gained to the students who necessarily don't read the paper or didn't go deep into the paper. So you kind of like, teach others a little bit about that topic. Important thing about the paper is you shouldn't repeat what we already discussed and taught you in the class. It should be an extension of that, okay? So don't just make sure that you have watched the lectures before preparing your presentations, because oftentimes there are people who don't really watch the lectures because it's not required. They have like an assigned paper, come here and start like teaching about the basics of cache and all, which we already covered that in the class. So be very cautious about what you're putting in your slides. Make sure that you have already watched the lectures, all the lectures fully before actually preparing your slides. You will be judged based on your presentation, the styles, the slides, and also the content itself. It's also a good way for you to practice how to present. So for many of people, actually, this usually is the first time, especially for undergrad students, first time to present and read the paper. So it's very important skill set that you're going to learn as a part of this. Since this is part of the lecture, effectively, it's important to have high quality lecture, presentations. Please use good visuals, spend some good amount of time on your presentations. You're going to be judged by everyone, including me. So people are going to grade your presentation, your content, and your style. And if you don't do a good job, you're going to lose a lot of points, and that will directly impact your grade as well in this course. So this is very important, both on your level of understanding, on other students' level of understanding, and your grade. So the three important things that you need to know. As I said, the goal is for you to read the paper in more depth. So try to spend time reading the paper. When you're reading that paper that you need to present, you also kind of need to read a few other papers. The papers that's kind of usually there's no one paper that is like built in silo. It's usually built on top of a lot of prior works. So it's a good thing to kind of like go a little bit deeper into those prior work as well. You practice your presentation skills. Other people who didn't read the paper will kind of understanding at high level. And then also this is a good opportunity for you to network and know a few other people, of course, not MSOL students because they do it alone. So guidelines. So use the slides when you're preparing your slides. You can, as I said, this is available, but generally it has to be 10 minutes long. If it's longer than that, you're going to lose points. Do not provide any sort of motivation or introduction of the topic. Oh, computer architecture is important or security is important. This is, as I said, this is built on top of what you learn in the class. So try to just describe the problem from the first slide and go through the problem. And don't just repeat what the paper already said or what we already said. Please just use your understanding and use that to present the papers. And then for the solutions, try to show the intuition. You don't need to go through the details of, like, let's say, for example, this particular algorithm or this scheme or that scheme. Give us the intuition that, okay, here's the big idea that this paper did. This is like what is new about this paper. This is how it's different from the rest of the works and so on and so forth. And you also don't need to really go through the details of the results. Just show us that it works. But then again, it's more about giving us the intuition and teaching us the important concepts in that paper. Your final slide should be like 2-3 discussion points. This discussion points helps you to interact with other students and let other students think about this problem a little bit more deeply. Since the ChatGPT era, typically this is generated by ChatGPT, but try to at least tailor it toward your discussion points. So just don't feed it to ChatGPT and say, okay, ChatGPT, give me 2-3 good discussion questions. Do something a little bit more meaningful. All right. So the feedback going to be a Google form that we're going to post. So everybody who's in the class or watching the lecture online going to submit a feedback for the presentations. You don't need to do it for every single presentation. I'm going to share you the details. So roughly between 8 to 10 feedback form you need to fill for the entire quarter. And then eventually I'm going to sanitize the feedbacks and share it with each group. But the grade's gonna be used for the presentation score, so you're gonna be reviewed by your peers. More details about the feedback gonna be posted on Campus Fire. Any questions so far? Okay. So we're gonna have paper readings as well. This is fairly optional, so this is actually one feedback I received. In the past, I asked students to submit a paper review for 2-3 papers per week. Not per week, but kind of like twice a week, per 2 weeks of every other week. What I did then after, again, ChatGPT era was I basically saw that this is meaningless because, again, essentially you put the PDF into ChatGPT and ask for the right summary and you submit that. So it's just meaningless work. So I removed that. But then based on some people asked that, okay, that's actually for those people who genuinely wants to read the papers, that was a good practice. So I'm bringing it back. So you have to actually do the paper readings. Of course, you can still use ChatGPT and it's your choice if you want to do that. We're not gonna grade based on what you've written. We're gonna just grade whether or not you submitted a PDF. So it's like 0 or 1 you're gonna get. We're gonna just check whether you submitted the right paper. That's all we're gonna check. So feel free to use ChatGPT if you want to, but if you want to learn and just spend a little bit more time, try to do that. Maybe you can even use ChatGPT to give you a little bit more insight, right? So you can read it and then ask ChatGPT to give you summary, and maybe ask ChatGPT to give you more summary. So try to use it interactively if you want to, but it's your choice of how much time you want to put in. I'm not gonna flag you if you use ChatGPT, but you're not gonna also learn anything for doing that. So you're basically wasting your time, but it's your choice. The paper list will be also published this week. We're gonna, as I said, 4 or 5 different categories. In each category, we're gonna have like 4 or 5 papers. You're gonna choose 2-3 papers from that category and submit a review. Okay. For those of you not very familiar with how to read the paper, generally academic paper, it's a very nice paper on how to read the paper. You need to have basic understanding. This is a chicken and egg problem. So if you don't know how to read the paper, you may not be able to read this paper too. But it's a simple paper, so hopefully you understand that. But once you understand this, then you can understand other papers. So it's gonna be helpful. But generally, it's a good thing. The way I do it mainly is, especially if you don't have like very significant amount of deep background on the topic, what I try to do is kind of like I try to kind of skim through the paper and try to understand the basics at a high level, and then I go back and try to read. And then, as I said, sometimes before understanding this paper, maybe you need to spend some time on understanding prior works or some related topics. So that's where, for example, things like, large language models could help you. Because, for example, let's say you don't know anything about this particular things, niche things that's being used in the paper. Maybe you can use these models to teach you or watch some lectures or watch some videos or read some books. Learn that and come back to the paper. But don't spend like 8 hours to understand a paper if it's like too rough for you. Try to kind of get the gist of it. Questions so far? Yes. Oh, no, you're stretching. No questions? All right. Okay. Participations. As I said, attendance is not required, is optional. But you can come to the class and ask questions. During the presentation, try to also ask questions. One thing I realized is that people get like shy of not asking questions during students' presentation. The whole point of presentations is being interactive. On Campus Wire, you can also ask questions. On Campus Wire, things are completely anonymous. I cannot see who asked a question. I cannot see who answered the question. So feel free to ask any questions that you want. You can ask groups. You can ask things about the lectures. You can ask things about the papers. You can ask things about presentations. You can ask things about the projects. You can ask things about general computer architecture and or security. So feel free to use Campus Wire, feel free to post a lot of things and ask a lot of questions. And not only just ask questions, try to answer each other's question. As I said, answers are also anonymous. So don't be worried about, oh, my answer is not correct and so on and so forth. Just feel free to share your thoughts, even if you're not fully sure that they're correct. We're always gonna like monitor them and edit them and correct them if necessary. But past experience has shown that you guys know what you're talking about, so you can always answer good questions and ask good questions. So please be active. If you're not, if like, personally a shy person, you don't want to ask questions during the lectures, Campus Wire is the way to go. MS Online students, for example, again, Campus Wire is a good choice for you guys to be active. For participation, there's no grade, there's no bonus. I've tried many different things in the past, none of them worked. So at the moment, I'm just like, take it easy. So you want to come, you don't want to come, that's your choice. If you want to make impressions, if you want to do research, if you want to ask me for letters of recommendations and stuff like that, you have to come to the class. If you're not coming to the class, and if I don't know you, I'm not gonna say yes to your request. So that's pretty very straightforward. But other than that, you can watch the lectures. I understand that some people learn by watching lectures offline in their own free time. So it's okay if many of you don't come to the class. All right, there will be one exam in this course on the last day of the class on Wednesday of week 10. Unfortunately, we cannot reschedule it. We cannot change the time. It will be in person on campus. MS Online students, it will be 24 hours on Wednesday. I'm going to post a little bit more details for them. But for on-campus people, you're going to come at 2 p.m. on Wednesday, and we're going to have the exam. The exam will be open book, open notes. It will be on Gradescope. Might be a combination of multiple choice to answer open-ended questions. ChatGPT won't be allowed, but you have access to the internet, and again, it's your choice what you're going to do, but it's considered cheating if you use it. The exam will be based on materials that I cover, plus the presentations that the other students will present, so both of them counts. And of course, computer assignments counts. The papers themselves won't be too hard, so we're not going to ask you something like very deep from the paper, but we're going to ask you something that's been talked about in the presentation. Main goal of the exam is that making sure that you watch the lectures, basically, because there's nothing else in the that kind of tie this course with the lecture. There's no homework per se, so we want to make sure that you watch at least once the lectures. And then, if for some reason you can absolutely not take the exam on Wednesday of week 10, do let me know ASAP. I'm not going to promise that we can find some options for you. So probably the option would be that maybe this is not the right time for you to just take this class, but at least let me know and see if there are some very, very exceptional, rare situations, we might give you some exception to take the class. If you're a CA students, I'm going to post this later once we get close, but you can take it from home if you're a CA students. So that's the only exception. All right, computer assignments. We're gonna have 4, hopefully, if nothing happens. Usually something happens at UCLA, like like fire, there is something always going on. So in the past, I always say probably nothing gonna happen, but I'm gonna say this time that something will happen. But if nothing happens, we're gonna have 4 CAs. So if you don't have any canceled class, so the CA is gonna be research-oriented class assignments. Actually, one thing that we're going to do, and we tried it on my undergrad class as well, is having a competition. So we're going to actually have 3 out of the 4 CA is going to be a competition. The first one going to be about a branch predictor. So you're going to design a branch predictor, and your branch predictor will be compared against branch predictor of other people. Whoever has the best performance is going to be ranked first. So we're going to maintain a scoreboard. And you're gonna see, of course, everybody if you submit, you're gonna get the full points. But if you have the higher rank, of course, you have the bragging rights and all that. We're gonna also ask the top 3 to kind of give us like a very short presentation of what they did. You need to also submit some form of a report for each design. I'm gonna share the details when we post that. Very interesting thing this year is that the branch predictor, which is the first CA they're going to be posted next week, actually. So there is an ongoing branch prediction championship going on right now. I think the deadline is April something. So it's actually right with the time that it's due for your project. So you can actually, if you want, you can submit your design to the competition as well. This is a worldwide competition done by ARM, and it's actually part of this very famous computer architecture conference called ISCA. So actually, if you submit and they chose your design, so they're going to select a few designs. They're going to invite you to go to the conference and present it. I think the conference is in South Korea or Japan. I don't remember, but it's a nice place. You can actually go, and also a good opportunity for you to network and talk to people. So you can actually spend some good amount of time on this if you want to. You don't need to submit it to this competition. We're going to have our own internal competition, but once I post this, I'm going to put the link for this as well. I think it's a good opportunity. You're going to do it anyway. So if you're a little bit more serious about it, you can submit it here. I can also help with the submission for especially those like top designs. We probably have a very good chance of submitting. Other question? No. Okay. No questions. Okay. But yeah, so this first competition is actually indeed a worldwide competition. So just FYI. So computer assignments, you can submit it in group of 2 if you want to. So or individually or group of 2. MSOL students, again, you should do it individually. But people on campus, you can do it in group of 2. Both people should submit the same code and same report. So both of you should submit. But we're going to have an running Excel sheet that you put your names and the kind of like the performance of your design. We're going to use that as a scoreboard. You can change your groups after each computer assignments. It's your responsibility to know that your group mate is alive and still taking the course. It's not going to be my responsibility to figure out who is working with whom. I'm going to just check every single, submission and see whether your name is there or not. If it's not, you're not going to get any points. If your name is there, great, you're going to get points. I'll grade each submission separately, as I said, and check the groups. And then make sure that you're not listed under 2 groups, obviously, right? So you cannot be part of 2 groups. If you are, then you're going to lose points. That's with the computer assignments. Yeah.
For that, can we just do the thing where we just add a person to our assignment because it's on Gradescope, right?
We can try to see if we can do it this way so that, but I think the easiest thing is that everyone just submit individually.
Okay.
Because when I'm downloading the grades, I wanted to see I can just see the numbers next to them. That's
Got
easy. Good. Yeah.
Exam, my user always say that the date will be June 11.
There is no final exam in this course. I think if it's
It
listed.
should be at the beginning of the June, the first week.
Yes, the week 10, I think, yeah, beginning of June. So there will be, in the finals week, there is nothing for this course.
Thank you so much.
Yeah. Good. Any other questions? Research, if as I said, any points you're interested in doing research, feel free to reach out. It's better to do it at the end of the course, so kind of know what's going on, and I kind of also get some impression from you. In the middle of the quarter, probably I'm going to tell you that just focus on the projects. Make sure that you do the projects well, and at the end. And again, if you do well in the projects, that's also a good indication for you to join our group. But the design of branch predictor, for example, itself is a very researchy topic. So it's not just about like writing good code. It's also about what sort of algorithm do you need to use and so on and so forth. For those of you, for example, interested in machine learning and intersection of machine learning with computer architecture and hardware design, very good opportunity for you to kind of bring some ideas from machine learning for prediction and so on and so forth. So a lot of opportunities across these competitions for you to kind of go a little bit deeper. Gradings would be 25% paper presentations, 40% CAs. If you have 4 CAs, it's going to be equally divided, and 35% for exams. And this will be 100% hopefully. We're going to do absolute grading. I'm going to reserve the top 2-3% A pluses. I'm going to just basically assign A pluses to the group that I feel like they deserve. Everybody else is going to get A between 93 to 100. From 93 down to 90, you're going to get an A minus. Basically, if you have over 90, you're going to get some form of A. Between 90 to 60, you're going to get a B. Below 60, you're going to get an F. Okay? Yeah, there's no C and D and all. PTEs, how many of you are not enrolled in this class? Okay. How many of you are in the waitlist? So those of you who raise your hand, are you in the waitlist or not? Like, how many of you are not in the waitlist? Okay, so yeah, so for those of you, we're gonna issue PT hopefully next week. So what's gonna happen with this grad classes is that there are other people who are gonna drop. Okay, so there will be lots of spots available in the next few. Could be now even because maybe some people are not liking the lecture. But but it's usually within a few days. So keep checking the enrollment. There will be more spots. I know that undergrads, apparently there is still a restriction. If that restriction stays, I'm gonna just give you PTEs. The restriction might be also removed. I'm not putting the restriction, it's not my control. It's just something that the department decided to do. That apparently there's some policy that you want the undergrads to apply for petitions to get into the grad classes. You can also do that, but I can also give you PTEs. For everybody else, if you have space, I'm gonna give you PTEs. Okay, so the only limitation for us is the size of the seat number, and that would be the only limitations. Until week 2, I'm gonna honor that. After that, I can also again issue PTEs beyond that. So I have few PTEs, but usually I have limited amount of PTEs, so I'm not gonna skip them all the way right now. I'm gonna save them. You're gonna enroll. If you cannot enroll, I'm gonna give you PTEs. Okay. Other notes, there's no reference book for this class. There are traditional computer architecture reference books that you can use. There is this computer architecture quantitative analysis by Hennessy and Patterson. It's a good book, a very relevant book. But generally, there's no one single reference book that you can use. There's no discussion sessions for this class. If it's listed, just ignore them. You don't need to go to them. I'm going to record all the videos, which means that your voice is going to be included on the videos if you ask questions. I'm going to post this on YouTube. So if you're not comfortable with that and you don't want your videos or your voices to be recorded, please do let me know so that I won't post those or somehow remove it. Otherwise, I'm assuming that everybody is fine with me that recording this class and putting it on YouTube. Okay. Of course, this class is based on academic honesty. So anything that is considered cheating, going to be, if we caught it, we're going to report it. So things like using ChatGPT for the exam or trying to copy each other's design and things like that. Of course, you're welcome to discuss things among themselves and then come up with designs, but try not to, try to design your own design for the computer assignments. If you want to share codes, make sure that shared code is properly cited and everybody knows what is being shared. And as I said, for paper reviews, I don't care about what you're going to use, but try to generally, as I said, this is the course that, it's not about me kind of forcing you to study. If you want to study, you study. If you don't want to study and get a grade, that's fine. I'm not going to block you. And then I already talked about MSOL, same things apply to you. If MSOL students, you watch this and you are not clear about certain things, let me know and I can happy to answer those questions. You can email me or you can message me on CampusWire, okay? All right, so let's have a quick break and we're gonna talk a little bit about more content. Is there any final questions about logistics? Yes.
Is there a TA at all or no?
There is a TA, but the TA is not gonna do discussions. She's gonna come and give you a guest lecture at some point. But they're gonna be on the campus for if you ask questions, you're gonna see that it's gonna be answered. Yeah.
If you're not enrolled in the class or we can't get on the wait list, are we missing out on CampusWire things?
On CampusWire, what I can do is I can give you the link somehow, or you can ask your friends for the join code. But I can you can also email me and I can send you the link for the CampusWire. Yeah. All right, let's have 5-minute break and then we're gonna come back and talk about. All right. So let's continue. All right, so we talked about the logistics. So let's a little bit talk about a little bit the content itself. The first question is, what is a good idea? Why we should do this course? In fact, actually, I mean, I'm assuming that someone just came from this way and then went out that way. That's very interesting. I forgot what I wanted to say. Yeah, so I mean, I'm sure that most of you are already interested in computer architecture for various different reasons and not want to know a little bit about security. But for those of you kind of like thinking about whether computer architecture is the right course for you, the interesting thing is that, interestingly now is a very, very interesting time to become a computer architect. Not necessarily for security, but it's even better. Someone started a game. It's even better to be in computer architecture security. I'm going to talk about that after this. But even computer architecture design is very hot topic right now, mainly because of intersection and role that computer architecture plays in AI and machine learning. Most of you probably follow the news. You know that now NVIDIA is like $1 trillion company. And this actually tweet was before this current administration. So it's dark ages. But it used to be like, NVIDIA's stock was growing significantly. It was actually within one day, they had $200 billion in share they got, which was basically bigger than the entire size of Uber, PayPal, Spotify, Coinbase, and Robinhood combined. What means that this effect of machine learning on hardware was very significant. NVIDIA is still doing very well. Of course, now everything is kind of like dropping significantly for obvious reasons. So now the question is, did I buy NVIDIA stock, given that I'm familiar with this topic? Unfortunately, no. But the reason is that it's complicated, and also like, I just know things and not necessarily use it. But why? So I think the important question for you guys is why computer architecture all of a sudden is a very important thing when it comes to AI. Is that if you think about AI, there are three things that is kind of have a key. There are three fundamental reasons why AI is where it is right now and why it's so successful. There are algorithms, data, and hardware. Okay, so there are three kind of pillars that cause AI. This causes AI boom. Algorithms and data, interestingly, has been around for quite some time, especially lots of these algorithms that these days we're using, many of them have been proposed and designed in late 80s and 90s. So many of the machine learning ideas are actually not necessarily very new. Data was something that happens a lot, and thanks to various different things, including the birth of internet and devices, all of us collectively generate tons and tons of data. That now we can see that how helpful it is, for example, for these large language models that they can be trained on this public data. But what really was the game changer in machine learning was in the 2010s era, that decade, where people actually tried to see that the machine learning model can be mapped into a GPU. And this is the birthplace of what we call an AlexNet model, which few very smart people saw that, actually a neural network would be very nicely fit into a GPU. Well, what that means is that now we can scale this massively, right? So we can scale this so significantly that it basically exponentially grow in like less than 10 years. So you're talking about billions and billions and billions of parameters. So we kind of started very humble beginning in like early 2014 and so on. And now you have all these like GPT models. So this is not actually, by this AI models, depending on which day you're taking a screenshot, it's going to be old. So for example, this is GPT-3, it's 175 billion, but GPT-3, nobody's using it anymore, right? So it's actually growing so significantly. So why we have this? Because there's this fundamental law that is no longer Moore's law. It's called neural scaling law, okay? So this neural scaling law basically tells you this, that the larger the model, the better the performance. Basically, the bottom line is this, that you provide more memory and more hardware, things get better. And that's great. That's great business for many people, for hardware designer, for architects, for machine learning models, and so on. So that's why GPT-2 is better than GPT-1, and GPT-3 is better than GPT-2, and GPT-4 is better than 3, and 4.0 is better than. What happens in these models is that they get more and more parameters, right? And for more and more parameters, you need more hardware, you need more and more memory. So for now, the rule of thumb is that if you can provide more hardware and you can architect and pack more things into your hardware, you're going to get even more powerful system. And that's why this is very lucrative business, because now they need even more. So that's why they need computer architects to give them this more. Yes.
Well, this might be a naive question, but how does something like DeepSeek, where they managed to get like a smaller model with similar performance play into it?
Yes, that's actually a great question. So this neural scaling law has recently been challenged with things like DeepSeek, because essentially what now we have seen is that, I told you that, more data and more hardware means better. Still that applies, but maybe more refined data means even better performance, which means that if I have more refined data, then I don't need that big of a memory and that big of a hardware and that fast of a hardware, right? So now what happens is that now the algorithms really now kicking back in, because really we're kind of pushing the envelope. We're reaching to the end of the technology of what we can push through. But still, you're going to see newer models with bigger and more parameters. But at the same time, there is of course, there is need for good machine learners and good algorithms. So it's not going to be just hardware that pushing this trend forward. There's going to be better data and better algorithms as well, for sure. Yeah, good point. So now the question is that now we understand why we need this. And as I said, this is like one of the hottest job at the moment. If you're some sort of a machine learning system engineer or hardware architect, you're going to be instantly hired by these big companies, especially if you know what you're doing. And you're going to be paid like $1 million kind of salaries these days. So how do we exactly make hardware better? There are 3 things that we do. The first thing that the most obvious thing is that we just pack more transistors. This is a picture of M3, M3 Pro, and M3 Max. As you can see, the difference between M3 and M3 Max is that M3 has 25 billion transistors, M3 Max has 92 billion transistors. So literally much bigger. So we actually pack more transistors into the system. And of course, when you have more things, then you can do more. We have more transistors, you can do more things. Not only more transistors, but more faster transistors. So there's this thing called technology. Like, for example, this one is 3 nanometers. Essentially, if I reduce the size of the transistors, I can pack more transistors. But not only I pack more transistors, each transistor gets faster, because essentially think about the distance that each electron needs to travel. I'm reducing that distance, which means that things happen faster, right? So this thing called channel is basically this number. So when you say 3 nanometers, it means that it requires 3 nanometers for one electron to go to the other side. So if I make it now 1 nanometer, then it means that 1/3 of this distance the electron needs to go. The speed of electron is the same as speed of light. So less distance means less time. So things can be switched much faster, right? So I can process things much faster, and that's the reason that we have better and better technologies. That's number one. The second thing, so the number one is really not what we're going to cover in this course, because this is more of a lower level VLSI, but there's also lots of exciting things happening here. But what we're going to cover is that not only we just pack more transistors, you also need to do something useful with this transistor, right? If I just give you, okay, here's another 200 billion transistors, if you don't know how to design them and how to use them, then it's meaningless, right? So you need to parallelize, you need to pipeline, you need to do lots of tricks in order to use this more transistors. Or if I tell you that you have faster transistor now, how are you going to use it? And still the question of the design. And that's where computer architecture comes into play. We're going to pack a lot of features, a lot of different things into our systems to make them faster. This is the design that we're going to see a lot in this course. This is a fairly modern Allo border processor called Boom. As you can see, it has kind of 3 big parts. There's a front end, there's an execution unit, and there is kind of a back end, a load store, and there's like an L2. We're gonna actually go through every single one of these boxes and tell you what they're doing and why we have them and what are the other options. But these features is like what's really make things more advanced. This is only the CPU. Computer architects is not just designing the CPU. There's lots of other things that we are doing and packing features and new things into the system to make it faster. How we actually do that? We are transitioning from a CPU-only system to what we call a system on a chip or more specialized system. So this is again from Apple. So as you can see, like in a state-of-the-art flagship Apple design has a CPU, has this thing called Fabric, which is kind of think about it as the substrate, as the connection. Then it has GPU, it has DRAM, it has neural engine, it has caches, it has these little things that are other features in the system. So as you can see that we no longer have just a CPU, we also have these newer components such as a GPU, or a neural engine that are designed to do something very specialized, right? So for example, neural engine is great for matrix multiplication, for neural network computation, and so on and so forth. And then you can see also like the close interaction between technology and computer architecture here that, for example, this Fabric allows you to connect these two at a very, very high bandwidth and very low latency connector. So there are these kind of things also going on. As I said, that's why you, as a computer architect, you don't want to just know one thing. You want to also learn a little bit about lower level and higher level as well, okay? So basically, these are the three main things that we are doing. So we pack more transistors, we put more features, and we specialize. Collection of these three is why we are making faster and faster computers. That's why NVIDIA is like pushing through new GPU systems and so on and so forth. That's what they do. That's these three things that they do. These days, they also use software as kind of like the fourth layer and making some changes in software to make their algorithms more efficient. And that's kind of like the DeepSeek also kind of within the same realm. So a collection of this with good software is making things faster and better these days. So that's where we are right now. And what we're going to do after this is that we're going to push this on all fronts. We need new specializations, we need new features, we need newer technologies, we need better software. We need all of that to make things faster. And that's what we're doing. That's what the industry is going at this currently. And they need a lot of people in all directions. That's why it's a very hot topic at the moment. Question?
What are examples of specific features that are packed in?
Oh, that's gonna be this course. You're gonna learn that. Yeah. Yes.
So we're also kind of nearing the end of Moore's Law, right?
We are kind of ending all of these technically, right? We really cannot push more transistors in, and that's a big worry. We still can push things. So 3 nanometer is kind of like a new thing. So we still can. There's after 3 nanometer is 1 point something, which we go with angstrom now. The nanometer is no longer like a good number, right? So there's another like 1 or 2 generations more. So there's still hope that at least 1 or 2 more generations we're gonna see after 3 nanometer. But afterwards we're not gonna see more. We're not gonna go through it for this course, but there are other things that we can do. There's big thing that we're gonna later in the at the end of the course when we have if we have time we're gonna talk about, and that is like chiplet design that we're gonna put 3Ds and put transistors on top of each other's. So there's these other tricks that we can do, but yeah, it's gonna end at some point. Questions? Okay. Cool. Okay, so what we're gonna learn? We're gonna, as I just answered Philip's question, we're gonna learn about this second topic. We're gonna talk about these features. We're not gonna talk mainly about a lot about specialization. So we're not gonna talk about like GPUs or accelerators a lot. There's other good courses at UCLA that talk a little bit about these things. So there's a GPU course, There's also a nice course on the accelerators that's being offered right now. So if you're interested in those things, I recommend taking those either in, in parallel with this course, as a separate course, whichever you think it's the best option for you. But I definitely recommend checking out those courses as well. We're gonna touch a little bit upon these more advanced topics, but we're gonna mainly focus on advanced features on the memory system and the CPU. That's the main goal of this class, okay? But there's actually also talking about, as I said, this course also has a component of the security. So once we learn these things, we're gonna also then shift our focus in the security aspects of the system. What we're gonna learn is that unfortunately the security becomes this kind of nuisance when we are talking about this excitement. So like, oh, we want to faster machines and so on and so forth. But boom, there is like an adversary that comes like using this exact same features that you put in order to make things faster. They're gonna use the exact same feature in order to attack your system. And when the system is no longer secure, then it doesn't matter how fast it is, right? So that's why we need to kind of take a step back and talk about those things. So that's why security is now becoming equally important, because all of these great things that we do, we should keep doing, but we should also consider security as an important aspect of things. So why kind of like, what is the relationship between this advanced market architecture and security? Unfortunately, and interestingly, it has the opposite effect, that we add more and more features, make the system more complex. As we are making the system more complex, it means that we are introducing new bugs to the system. And that's exactly what you shouldn't do for security. For security, you have to have simplicity. You have to have simple designs. You have to reduce as much as advanced features as possible. But on the other hand, you do want those advanced features to make your system nicer and faster. Another thing that we do in our computer architecture systems is that we love to share things and kind of overlap things, because that gives us efficiency. But this sharing and overlapping means it's terrible for security, because essentially it means that now adversary has access to a lot of things that it shouldn't have, right? So if I share the register file between two processes, it means that if one process is an adversarial process, they have direct access to reading things from the victim process, right? So when I share things, it means that I have more opportunity, more channels available to the attacker. And we're going to learn this thing called side channels, and you're going to see that how attackers can use these side channels in order to attack our system. So unfortunately, you can see that how these are two exact opposite directions. So that if you ask someone from security, basically every decision that these big companies are making is an incorrect decision from the security perspective. So what we should do is that we should, of course, try to converge these two, right? So we cannot have systems that are secure or systems that are not secure. We need to find, we need to find designs that are both performant and secure, right? So this is the kind of the goal of a security researcher, and that's what we're going to do in this class. So we're going to learn these vulnerabilities. We're going to learn how to solve them, and you're going to also learn how to use hardware also even to solve software vulnerabilities. So one role of the hardware is also solving some of the vulnerabilities that we have in the software. And as I said, the security part of this class is going to be mainly the second half of the class, and going to be mainly based on papers that you're going to read. So all the 5 categories that we're going to have our paper presentation is going to be about security. So that's how we're going to kind of divide this class. All right. Any questions so far? Cool. So let me kind of from the rest of this lecture, I'm going to just briefly go through some kind of fundamental basic concepts that you probably most of you know. But we're going to go through it, and then next lecture, I'm going to start talking about advanced computer architecture and out-of-order processor. So what are the common things that you're going to repeatedly see in computer architecture? So one thing that interesting about computer architecture is computer architecture is really a systems problem kind of thing. So lots of these optimizations you're going to see is that systems optimization. It applies to CPU, but you can think about it that it can apply to the operating system. It can apply to the software. It can apply to many even non-cyber problems, like regular problems. So what are those? Actually, let me ask you, what are the main principles of a computer architecture? Let's see if how many of you can answer those questions, can name these main principles. Yes.
Throughput.
Throughput, which means, can you explain what you mean by throughput?
Just like how much stuff can get done in a certain amount of time.
Okay. So you want to increase your throughput or you want to reduce your throughput? Okay, increasing throughput, okay?
I'd say like the IPC,
Uh-huh,
better metric of throughput,
okay, So-
instructions per clock.
okay. But so the question that I'm asking you is, what are the big ideas in computer architecture? Like, what are the main things that like we try to do to make, so I want to make my computers faster, what do I do? Yes.
Parallelism?
Parallelism, right? So one big thing is we parallelize things, right? So as you more parallelize, things get faster, obviously.
Pipelining,
Pipelining is another one. Can you explain what is a pipelining?
basically instead of having one huge task, kind of like splitting them into like more sequential.
Yeah, and then try to overlap them, right? So if you can overlap them, then yeah, pipelining is another one, yes.
Caching.
Caching is another one, yeah. Can you explain what is a caching?
Caching is when we store memory or things like instructions that we often use closer to us, so that we can access it faster, because we'll know we'll be using it more often, speeds up our overall process.
Okay. Aruna?
Superscalar,
Super scaling, what is super scaling?
is just making wider so we can.
Yeah, okay, self, good, yeah, it's kind of like a parallelism, but it's more of like advanced version of parallelism, yeah.
Like simplicity, what I mean by that is that like, if I can like use one multiplex two different paths as opposed to using two different ones, like I'll take that.
So I simplify my design as much as I can, yeah. Hayden, you have something?
Oh, like out of order execution.
Out of order execution, okay, what is that?
Because like when you're processing instructions, it might be wiser, like if you're waiting on one, you can fulfill a process for something that might not be related to that.
Jacob?
Prediction, like branch prediction.
Prediction,
Prediction or any kind of speculations.
Yeah, so we speculate, we don't, like, we make some guesses and we run things and see what happens, okay, yeah, yeah. Multi-core, okay, so you add, so we're now going from parallelism to superscalar to now multi-core, great. Anything else?
Power consumption.
Power consumption, okay, what do we do?
Relate to the computer architecture, would you say, or not so much?
So power consumption, we do what with it?
Was like minimizing like.
Minimizing
consumption for,
it,
like,
yes, we want to minimize it, but let's say if I have a design that runs faster, but it's more power consumption. What would you do? Would you not use it? So if I say, oh, I have
Depends
this
on the
great
application.
feature that makes things much faster, would you use it or not?
It depends on the application.
Depends on the application, exactly, right? So there's some applications you want to use it for, some not, right? Anything else? Good, we kind of cover, I think, almost all of it. The first one that nobody talks about is abstraction. And kind of we talked about simplification, which was nice. So abstraction is that we love abstraction. As computer scientists, we love abstraction because abstraction allows you to focus on one thing, but not like completely in a disjoint way. You kind of try to simplify other things around it. So when we are focusing on computer architecture, we know that there's going to be a layer underneath it and a layer on top of it. But what we see is that we're going to say that, oh, operating system is this black box that magically kind of gives us this and that. And transistors are these, again, the magic things that we're going to say that, oh, run this instruction and it's going to run this instructions for us, right? At the architecture level, we don't need to know, I don't know, the quantum effect or I don't know, like, the type of the CMOS or the technology or the process variation and all that. I just know that stuff runs, right? So that's all I know as an architect, right? And similar, like at the software layer and the, like, if you're 10,000 view of like I don't know, machine learning data scientist, all you know is there is a Python code. You don't even know how things are running, right? So these are kind of like things that we do and it works very well. Nice thing about learning it though is that you want to break these abstractions for yourself. So when you're learning these things, don't try to just purely abstract things. Try to abstract things away and then try to know that you have some basic understandings of every layer because it's very important for you to learn this. Another thing that we love to do is making the common case fast, okay? So computer architecture is all about how can I make my common case the fastest? I'm not going to make everything fast. I'm going to make my common case as fast as possible. And the idea is that this common case happens so often, then I'm good to go. The third one is parallelism that we talked about. The fourth one is pipelining we also talked about. The fifth one is prediction or speculation, which also we talked about. And then the last one is memory hierarchy or caching, which we also talked about, because memory is generally is this thing that can be slow or big. If you want to both fast and big, then we do this hierarchy of things. And then last thing that I kind of talked about before is a specialization that we no longer want, because generalization is great because it gives you everything, but generalization means that I do everything kind of at same speed. If there are things that I want to do really fast, I can actually design my things to run that very, very fast. So that's why instead of now having just one unit, I have many, many units, and then I have one unit that kind of distribute this work to those units. So that's kind of like now the common practice in computer architecture. That's why we have GPUs and neural engines and so on and so forth. All right, any questions about these ideas? So as you will see, is that many of these things that we're going to talk about, especially in the next few weeks, going to be based on one of these things that we see. It could be a combination of them, it could be one of them, but you will see that there will be lots of these things you're going to see. The other question? Okay. All right. So there are four. So let's talk about parallelism. So there are four parallelism that we'd love to have, and we're going to quickly talk about them. And then as we're going to talk about out of order execution, you're going to see them. So there's DLP, ILP, TLP, and RLP. LP means level parallelism. So DLP, for example, is data level parallelism. Okay. Does anybody know what is ILP? Yeah. Instruction level parallelism. What is TLP? Yeah. Thread level parallelism. What is RLP? Not register. Go higher. It's a rack level parallelism. So we want to actually do it in multiple servers. So let's see actually what these are. Before actually talking about these DLPs, there is this taxonomy that we're going to see a lot in this course as well. So you can have either single or multiple instruction streams, and you can also have single or multiple data streams. So you can have SM or SM. So the simple one is SISD. So single instruction, single data. This is your good old small core. It's like take one instruction at a time and takes the data with it and run it. That's your SISD. That's most cases, that's what you really want and we will have. Most of your low-end devices has SISD. It doesn't really need like, high-end servers and so on and so forth. Then you're going to have single instruction, multiple data. This is what we call a SIMD machine. A great example of a SIMD machine is a GPU. So GPU have one instruction, but has tons of data. So for example, you want to multiply two big, matrices, right? Matrices. So the instruction that you're going to run is multiply. So there's single instructions, but you have a big vector here and a big vector here. So that's why it's single instruction, multiple data. That's why GPU is designed to have big register files. They have small core, but like big, execution units and execution lengths. Then we're going to have MIMD. So this is multiple instructions, multiple data. So I run multiple different things on multiple different streams. This is what we call a multi-core or superscalar in some cases. So superscalar is single core that has multiple lanes that can run parallel instructions. If I now have multiple cores, each core is also superscalar, then I'm going to have a MIMD system. So it's multiple instruction, multiple data, which means that I run multiple programs at the same time. These programs may or not be related. Sometimes I can divide one program into multiple, threads. Sometimes I just run two separate programs. So for example, in my computer, I open Zoom and I open this, Microsoft OneNote at the same time. Both of them are running at the same time because one is running in one core and the other one is running on the other core. If I didn't have MIMD, I couldn't do this. So I could just run Zoom or OneNote. You can also have multiple instructions, single data. That's usually not happening. It's not the best system that you can have because typically you're either limited by data or you're limited by data and instructions. You're rarely limited by instructions, but in certain cases, for example, for crypto engines and all, you may want to have a machine that can run multiple instructions on the same data all at the same time. So think about like, if I want to do cryptography, this could be a good option for me. So we're gonna maybe talk about this. We're going to talk about the MIMD system, so keep that in mind. All right, so let's talk about this DLP and so on. So what is a DLP? What is data level parallelism? So think about an adder, right? So I can add 2 bits and get a sum, right? But instead of adding 2 bits, I can add 8 bits. Or I can add 4 bits and get a 4-bit sum, okay? This is what we call, this is like a very simple, probably first thing that you probably learned about logic is data level parallelism. That you don't do things in 1 bit, you do things in big bits, right? So you do it in bytes or multiple bytes, 32 bits, 64 bit, 124 bits, sorry, 128 bits, and so on and so forth. That is what the data level is. So essentially, almost every machine, even simpler ones, use data level parallelism because otherwise it doesn't make any sense. But what is the trade-off? Of course, means that I need to now copy more logic. So remember I told you that I have more transistors? That's where I can use those transistors, right? I can make my adder bigger so I can add more things faster because now everything happens in one cycle, but now I can add more things to it, right? And of course, you might ask that, okay, what is the limit? The limit is where I'm going to use this in real world. That's why machine learning is this godsend to computer architects, because before machine learning, you had a big multiplier, but what are you going to multiply? 2 numbers that you don't care. But now I'm telling you that, oh, you can actually multiply this very, very large vector that is, I don't know, a natural language processing, a text, and you can multiply it in this very large language models, and boom, it's going to give you an answer, and people are going to use it every day and every second. Then I'm going to say, okay, I have a solution for you, and you're going to give this to them, and they're going to be very, very happy, right? So DLP is actually at the heart of most of these parallelism. Then you're going to do what we call an ILP. So on top of just doing simple things, you're going to run multiple instructions at the time, right? So you have seen this in your fundamental computer architecture courses, that you will see that, for example, we can run these things all together, like for example, these different things all together at the same time. Of course, a big thing when we are talking about all instruction level parallelism is that if I want to run these things, then I need to be worried about a lot of things. So for example, in this example you see here, you see that R1 here is the destination register of this instruction, but it's actually the source register of this instruction, which means that this instruction is kind of implicitly or explicitly, actually in this case, is dependent. So I cannot run A and B at the same time because I need to have the results of A to actually run B. So I cannot just blindly run these things. But if for somehow I can change this and make it this way so that maybe instead of R1, I have R2 and R3, then I can easily run these 3 things all in the same 3 different lanes in my system. So how do we get from here to here? There is like a full course on it, right? So there's like, all the basic computer architecture is going to talk about like renaming logics and forwarding and data hazard and control flow hazards and all that we covered in our basic computer architecture. And I'm expecting you to know these stuff. But just generally keep in mind that ILP is gonna, if I can run this, then I can run them all together in one cycle. So it's as if that I'm basically, instead of like 3 cycle, 1 cycle, 1 cycle, 1 cycle, now there's only 1 cycle to run all 3 together. And each of these are not 1 bits, they can be multiple bits. So I have DLP here, this is my adder, but now I also run them together. So this is my instruction level parallelism, okay? And then I can then do the pipelining to make this even faster. Again, if you remember what pipelining works is that if, let's say, for example, I have a simple processor that has 5 stages of the pipeline, what I can do is that instead of saying that, okay, I run this, then run this, then run this, I can overlap them, right? So I can say that, okay, while this first instruction is here, like while this first instruction here, I can run this next instruction. While this instruction goes to the next stage of the pipeline, I can feed this here and I can bring in new instructions. So at any given point, I can fill all the units in my processor to run things in parallel, right? So this is how we can actually make things much, much faster as well, right? And again, if you're not too familiar with this notation, don't worry about it, but just know that you know what's going on with pipeline, okay? All right, so then beyond pipelining, what we do. So that's how we make our systems faster. So we have, instructions that runs as much as possible. But one program can only get faster to some extent because you're gonna have dependencies between instructions at some point, right? So you cannot run the entire program all at once, right? Because you have instructions that you have an if then else that is depending on something else. So you need to have some form of a sequence. So how do I actually leverage from even more parallelism? And that's where TLP comes into the play. That I can actually run multiple different programs, or I can write the program such a way that it can be parallelized into different things, right? So again, a good example is matrix multiplication, which I can then kind of divide this into smaller units. Usually we call it processing elements, and do this partially, right? So I can, instead of multiplying A and B or adding A and B, I can say that, okay, there is a partial A, A1, B1, A2, B2, A3, B3, and so on and so forth. Then I'm going to have these, partial elements. And then I'm somehow going to get these partial elements and kind of add them together and so on and so forth. So I can kind of do this gradually to make a big system, right? So I can do this in multiple threads. So each one of these, we call them like a thread, depending on how do we run this. If it's like a multi-core system or multi-processing element system, I can run this in multiple threads and then get a much faster system down. And this is kind of like the multi-core model or the GPU model. The GPU model is more of like instruction streams. The multi-core model is really just independent instruction stream. Remember that multi-core model was MIMD, multiple instructions, multiple data. GPU was SIMD, it's a single instruction, multiple data. So this is a single instruction, multiple data. This is MIMD. So this is different instruction, different instruction, different instruction, different elements, right? Typically we have each core has 2 threads, and you usually have 4 or 8, sometimes 16. So we're talking about 32, 64, something like that number of threads that you can run. Another thing that you can do on top of thread level parallelism is multi-threading. So what is a multi-threading? So you're going to have a bunch of different options if you have different programs, okay? In the normal systems, the way it works is that so let's say I have a program, a green program and a yellow program. Each one has 4 lanes, so they're super scalar processors. So if I have only a single machine that can only run 1 thread at a time, here's what I'm going to do. I'm going to run, so each of these columns is 1 clock cycle, okay? So I'm going to run program green for 6 cycles. Then I need to switch from program 1 to program 2. This is the process we call context switch. So we need to give the control to the operating system. Operating system going to do lots of stuff and then going to allow the second thread to run. Okay. So this is what happens in a very low end processor. Okay. Then if I don't want this involvement of the operating system every time that I want to context switch, there's this thing called coarse grain multi-threading, or CMT. The way CMT works is that this switch between program 1 to program B can be handled by hardware. So I can instantly switch between the programs as much as I want. So I kind of save this kind of time. So I can run this program and then run this program and then run this program and then run this program. This is called coarse grain multi-threading. So I can run multiple threads. As you can see, I'm not really doing it in parallel. I'm doing it serially, right? But at least I can switch very fast, right, between them. Then you can say that, okay, why don't I do it even more fine grained, right? So instead of doing it every, let's say, 6 cycle or 10 cycle, if I can do it every cycle, then I can have even finer grain multi-threading. So this is what we call fine grain multi-threading, which means that at every cycle I can run each of these applications. Why do I want to do this? Because, for example, the idea is that at every cycle I can find the most important or the ones that is most critical and run that. And now that we have And now that we have fine grain capabilities and coarse grain capabilities, I can do what we call simultaneous fine multi-threading or SMT, and this is the gold standard. This is most of the systems do it this way. Is that I can take an instruction from program A, take another instruction for program B, and take another instruction for program C, and put them all into the same pipeline. Okay, as long as I have lanes, different lanes, I can run it this way, right? So this means that now if you look at the number of white block, which is unused blocks, you can see that the utilization of this simultaneous multi-threading is significantly better than all the other, which means that I can finish my program much faster, right? Utilization means lower, better power efficiency and faster time. So simultaneous multi-threading is what we do on top of all the things that I described. So I want to do ILP and DLP. ILP is this, right? So thread level parallelism, but then I also do it with combining threads together, and that's why it gives you the thread level parallelism that we are talking. Okay, questions? This is, by the way, sometimes called hyperthreading. So if you see the word hyperthreading, it's the same as simultaneous multi-threading. Okay, but just an FYI, and you're gonna see it later, but this is terrible for security. Why? Because now green and red are literally sitting on the same physical hardware. And now think about the red is actually a malicious process, and green is a victim. So red can actually read a lot of things from green that it shouldn't. This one actually, in fact, is the safest in terms of security, because essentially at any given point, you only run things and you can clean it up, right? So you can actually delete sensitive information before feeding it to the next. So even if the yellow is a problematic and malicious program, it doesn't see anything about anybody else, but you can see that this is the slowest, right? So that's the problem that we are facing these days. All right, and then what is RLP? As I said, rack level. So now we have thousands and thousands of computers. So why not using them all at the same time? So that's where think about like AWS, Amazon Web Services. Think about the way that we train. Think about OpenAI, then the way that we train ChatGPT or Claude or whatever. They're all using a large scale number of servers connected to each other, constantly sharing data to each other, to make a training algorithm, for example, much faster, right? So this is the next level, and there are a lot of people nowadays working on this, and it's actually also very, very exciting line of research for many of you that you can think about the equivalent of bits in DLP is now programs or virtual machines in RLP. So if I can run multiple things at the same time, I'm gonna get rack level parallelism. All right. There's also a new thing called accelerator level parallelism, which means that if I have other components, right, I can also like feed this and run them at the same time. So I can have what we call an ALP. But ALP is really literally TLP, right? So thread level, if you define your threads as anything that can be run on different parts of your system, then ALP and TLP is essentially the same thing. But if you want to be a little bit more fine-grained, you can distinguish between TLP and ALP if you want to. Okay? So what is our focus? I think we are almost the end. We're going to focus on an advanced out-of-order multi-core system with several levels of cache and many optimizations. In fact, the design of this out-of-order will be part of one of your CAs. This is the non-competition one, and it's going to be probably like the most difficult one in terms of time. But you're going to actually go through the whole design yourself and you actually design it. You're going to design it in C. You're not going to design it in Verilog or anything, but you're going to actually learn a lot of these features when you're designing that. We're going to use Boom Core. Boom Core is this design. It's an open source design. And we're going to see this a lot. Actually, in the next lecture, going to be about the front end design of the Boom Core. Boom is based on RISC-V architecture. We're going to focus on the third generation V3. It's actually, the full name is Sonic Boom. There are tons of interesting documents about Boom and different Booms, version 1, version 2, and version 3. So we're gonna actually go through this as we're doing the lecture in the next few weeks, but also feel free to go and, educate yourself a little bit. So in the next few lectures, as I said, the plan is I'm gonna go through these components. One or two lectures on this, one or two lectures on this, and one or two lectures on this. And you're gonna see different things, including the front end, back end, and so on and so forth. The good reminder for you is that review the content of a basic computer architecture class, because we're gonna dive very deep and very quickly in these topics. So if you need, I think now is a good time that you don't have anything else to do. Go and check this course content out, or just go back to whatever documents or notes you have from your undergrad level computer architecture that you have taken with whichever university that you were at. And yeah, that's it. Next time we're gonna talk about front end of Google. All right, thank you guys.
Yeah.